I wanted to talk about some work that I'm working on that's almost done, but I'm really excited about, so I wanted to talk about it. It's about generative adversarial networks and about discussing some of the issues they have and how we can mitigate those issues. And our model is titled Semi-Implicit Generative Adversarial Networks, and I'll describe it and say what it is. This is joint work with Francisco Ruiz and David Bly, who are both at Columbia, and also Michalis Titias, who's now at DeepMind. So I'll start by discussing usually what we want to do when we do deep generative modeling. We have this unknown distribution P of X, and all we have, the window we have through that distribution is a set of data points, x1 through xn, and I'm calling here their empirical distribution, P subscript D of X. And what we want to do is density estimation. We want to find a proxy for P of X. And usually the approach is to have a parametric density. So you'll have P theta of X indexed by theta, and then you would want to find the parameters theta of your model such that it ends up being close to the unknown distribution. I'll define what close means at some point. There are two main paradigms currently in doing this in the deep learning community, which is the variational autoencoding approach or the generative adversarial network approach. The VAE approach, I put a picture of Hinton and Fisher because it describes mainly the two tools used in this approach. So in a VAE, you would define your model P theta of X as an infinite mixture. That is, if your latents Z are continuous. And what that means is that you would sample from this model by first sampling a latent variable Z from your prior P of Z, and then conditioning on that latent variable to draw a sample from the conditional distribution, often called the likelihood. In a VAE, the likelihood is parameterized by a neural network. So you would have this deep neural network, often called a generator, that takes the latent you have sampled and then spits parameters of an exponential family. This is a general description of densities for the data sets we encounter in practice. For example, Bernoulli or Gaussian or Poisson or whatever distribution you have, you can encapsulate them usually with the exponential family. And in a VAE, it's just take a latent, put it through a neural network, and get your distribution. And the key ingredient for learning is maximum likelihood, invented by Fisher. And what that consists in is you would find the parameter theta that maximizes your log density. The problem here is that this is intractable because, remember, we defined it as this integral, and there's no way you can get this integral in a closed form formula because we used neural networks for expressivity. And so the way around this is to, instead of maximizing the likelihood directly, you maximize a proxy objective, which is actually a lower bound to this log likelihood. And it's called the evidence lower bound, which is defined as follows. You have the first term, which tries to find the parameters theta and phi such that you fit your data well. And then the second term is some regularization term for the auxiliary parameters phi that prevents you from fitting just a delta Dirac function on the posterior. Okay, let me discuss the lingo first. We cannot learn the log likelihood, so we have to maximize this elbow, and maximizing the elbow involves coming up with this auxiliary distribution, Q phi of Z given X, which is an approximation to your true posterior, the conditional distribution of your latents given the data. And so you will have to also find these extra parameters. But your true goal is to find theta. And so find theta by maximizing a lower bound to the log likelihood, and it boils down to running through this optimization procedure. Take a gradient step to get update for phi and both phi and theta simultaneously. The problem with this is that you won't be able to learn a good set of phi parameters. Your posterior usually tends to automatically collapse to the prior P of Z because of the regularization term, the KL Q phi Z given X to P of Z tends to go to 0 very quickly during learning. And what that means is that you haven't managed to find latent variables that are descriptive of the data, which is bad because it affects also your learning of theta. And another problem with VAEs is that they tend to generate blurry samples, and that comes from the fact that they want to maximize the likelihood. They're maximizing the elbow, but the goal is to do that such that you're maximizing the likelihood. And when you do that, you tend to want to cover all the data. And when you're doing that, you are losing in your sample quality. But there are advantages too. It's not a bad thing. It has actually done well on many tasks. And their main feature is that they allow you to do scalable and efficient inference. This distribution, Q phi Z given X, is parameterized by a neural network as well that takes the data as input and outputs the parameters of the distribution. So that is very efficient. So you can learn models that have latent variable for each data set very efficiently. You can imagine if you have a large data set and each data point comes with a latent variable, you would want to have an efficient procedure for doing posterior inference, for example. And so VAEs give you that, which is really cool. And what they also give you is that you can tractably estimate the log likelihood. And that is good because if you have a way of doing that, then you can compare different VAEs and tell which one is better in a principled way. But we, again, have this problem of blurriness and difficulty in learning meaningful latents. The second approach is the GAN approach, which was invented by Ian Goodfellow. Okay, let me stop and say I don't condone violence. This was just for illustration purposes. It's the main learning procedure used in GANs, which is adversarial. So let me start by defining what GANs are. Remember, our goal at the beginning was to say, how do we approximate this unknown distribution P of X? And then we use the parametric distribution P theta of X and want to learn theta. Here in the GAN framework, your model P theta of X is defined through a sampling procedure, which is a way of defining distributions as well. And what the GAN does is that, okay, you define P theta of X by defining how you get samples from it, and you get samples from it by sampling a latent variable Z from some prior distribution and passing that through the neural network and get the output of the neural network as your sample. You can say, okay, this is the same thing as the VAE. It is not, because what the VAE would do is, okay, sample Z from the prior, pass it through a neural network, but instead of getting that output as your sample, you add noise at the output. That's what a VAE would do. And so you would have a tractable density, which you don't have here in the GAN setting. So the likelihood in GANs is undefined. Because it is undefined, we cannot do maximum likelihood. So the proxy in GANs is to do learning theta by classification, or also called adversarial learning, where you would introduce, again, these auxiliary parameters, which are these auxiliary parameters phi, which are the parameters of a classifier that takes the true data, remember, which follows PD of X, and then data generated from my model and compares them. So that's what this objective is doing. You would minimize with respect to theta, because when you do that, then the classifier wouldn't be able to tell whether what you have generated is looking like the true data or not, which is your goal. You want to learn theta to look like the true data. And then you maximize with respect to phi so that the classifier gets better at distinguishing the two. The benefit of GANs is that, like VAEs, you have an efficient and scalable way of training, which we care about because we deal with large data sets. And they're also known for having this excellent ability to generate good samples that look exactly like the data you observe, which is also something that's desirable for when you're doing density estimation, because that's indication of the fact that you're learning a good theta. But we will see that there are some disadvantages. The main one is this thing called mode collapse, which is that the P theta of X that you learn by fitting a GAN has low support. What I mean by that is that it doesn't cover all the modes of your data, and that is a bad thing. Another disadvantage is that because the likelihood was undefined, we won't be able to estimate log likelihood and compare different GANs. Usually people use perceptual quality measures such as inception scores, but there are many flaws to inception scores. So ultimately we would want to be able to have ways of computing log likelihood. And another thing is that the training is prone to instability, but that's expected because we have this minimax procedure. So people have come up with hybrid approaches where you combine ideas from VAEs to ideas from GANs to make up these generative models that should be doing better. And one set of approach is to use GAN ideas in VAEs, and what that boils down to is, for example, replacing the KL term in the elbow, remember this one, the regularizer there, the KL regularizer, which is the one that causes the collapse problem that I mentioned, is to replace that with a discriminator, for example. People have done that, and that avoids posterior collapse effectively. And if you want more details, you can look at these two references that I added there. The second hybrid approach is to use VAE ideas within GANs, and what they do there is try to have more meaningful latent variables by adding an encoder. So you have an extra set of parameters on top of your model parameter theta and your classifier parameter phi. You have an additional set of parameters that takes data and gives you a meaningful latent variable. So those are, for example, approaches in the Ali GAN architecture or the BAI GAN architecture. And there the modification is that you train the encoder and the generator to fool the discriminator, which would now take pairs XZ instead of just taking data X. But before doing that, before trying to combine GANs and VAE, let's think about what we want. So we have several sets of desiderata. We want high sample quality because we want to use these models to generate data from it, and GANs give us that. We also want high sample diversity. High sample diversity, we want to learn distributions that don't have low support. We want them to cover all the modes of our data distribution. So we want to avoid what the GAN is doing because of that. And we also want to be able to compare different generative models. And we want to do that in a principled way. So we want to be able to have a way of approximating log likelihoods as is done in VAEs. So what we propose here is, you can think of it as a hybrid, but what it is that we use the same model as in the variational autoencoder. What that means is that you would define your p theta of x as this infinite mixture, the integral, and then you would train that using the same procedure as the GAN. And the ingredients we use, I'll discuss them shortly, is entropy regularization and Hamiltonian Monte Carlo. And what you get when you do this, I'll show some empirical evidence, is you get samples as good as the GAN, you get tractable likelihood estimation for evaluation and comparison, and you get stable training procedure as in the VAE, and you get sample diversity because of this entropy regularization thing. So this seems to fulfill our desiderata for generative modeling. Let me talk about it in more detail. Our model here is this infinite mixture, which is very flexible. The prior is, as usual, it's a standard Gaussian. And the likelihood now, instead of just being the output of a neural network, you add a noise at the output of the neural network to define a density. And you learn your parameters by adversarial learning, so you're classifying samples from your model and samples from the data. But we also added this extra regularization term using entropy regularization. And what that does is that if we only focus on learning theta by classification without this entropy regularization, we wouldn't be able to cover all the support, because remember, that's what the problem of GANs is. And so the natural thing to do when someone tells you, I have this model that's learning low support distribution, is to say, okay, increase its entropy. That's what entropy, that's by definition what entropy does. And so it was natural for me to be able to do this, but then if you just do entropy regularization in the usual GAN model, you wouldn't be able to have a tractable way of estimating the entropy, which is why we needed to add noise at the output of the generator. Remember the neural network that defines how you sample from your model. And so here you can say, okay, the entropy is still not tractable because P of theta E is not tractable. But for learning, we don't need the entropy to be tractable. We just need the gradients to be tractable, or at least approximately tractable. And they are here when you define your model by having noise at the output of the neural network. And so I'll show some empirical evidence for details. I'll refer you to our paper that's going to be on arXiv very soon. But I just wanted to show you that when you do that, you're actually not losing sample quality or all the desirable properties of GANs. So here what I'm showing is a synthetic experiment on density estimation where we formed a distribution P of X that is a mixture of 10 two-dimensional Gaussians that are organized on a ring to make it more complicated. And then we draw 5,000 samples from these distributions. Then I train a GAN on it, train a semi-implicit GAN, psi-GAN, without the entropy term, just to see what we get when we add noise at the output. And then train a psi-GAN with the entropy term. And what you can see is that the GAN, you can say the GAN can capture this distribution. It's just 10 modes, and that is true, it can. But what I did was try to see whether the procedure we have just defined is able to fight mode collapse by choosing the settings of the GAN such that you would have collapse in this setting. So you miss 4 modes out of the 10, and then now use the same settings to train psi-GAN and see if you can avoid that. And you effectively can. When you don't have entropy regularization, when lambda equals 0, you capture 2 more modes than the GAN, and that's because you add this noise at the output, which gives the algorithm ways to explore the data space. And when you have the entropy regularization, then you capture all the modes, because that's what entropy does. It covers all the modes of the data. Another experiment we run is what people typically do in mode collapse in GANs research, is to compare the number of modes captured between different models. So I did that same thing here, exploring different values of lambda and seeing if the behavior depends on the value of lambda. So I considered MNIST, which has only 10 modes, and another version of MNIST, which has more modes, and it has 1,000 modes because we stack different digits in MNIST. We stack 3 digits in MNIST, and each one will be 1 channel. So you would have this data set that has 3 channels, and that looks like MNIST. What I'm reporting here is the number of modes captured, but also the KL divergence, which tells you how good your approximation is when compared to the truth. And what you notice is that for all of them, because MNIST has only 10 modes, all the models capture the 10 modes, but then you notice that the psi-GAN actually manages to learn a more faithful distribution of the data, as evidenced by these lower KL scores. But now on the stacked MNIST, which has a higher number of modes, it has 1,000 modes, the GAN can only capture 317, and that is not the case for the psi-GAN, which manages to capture, say, 999 as soon as lambda is set to a positive value. And also, you can see that the quality is better in how you achieve lower KL scores. Another thing we looked at, and that I think is interesting, is to show that actually mode collapse in GANs can happen even when you have a small number of modes, but have imbalance in the data. So what we did was take MNIST, which has only 10 modes, so it should recover all the modes. But we then created several different versions of MNIST, each one with a different level of imbalance by, say, undersampling some of the digits to make the data imbalanced. So we have 10 different MNIST data sets. And for each one, I record the number of modes captured by each model, GAN, psi-GAN, for different values of lambda. And then I also record the KL divergence, which tells us how good what we have learned is. And what you notice is that for the DC GAN, as the level of imbalance increases, which is from left to right, then it loses some modes, which is decrypted in this descending trend. When you use psi-GAN with lambda equals 0, meaning what you only did is change the GAN by adding noise at the output of the generator, you manage to do better than the DC GAN, but you are still losing some modes when the imbalance becomes very severe. But that is not the case when you set lambda to a positive value. So here I set it to 0.1, and it is robust to imbalance in the data. And the same behavior also happens when you look at the KL divergence. Because if you look only at the left plot, you can say that, okay, maybe it's covering all the modes because it's just putting noise everywhere. But that is not the case, which you can see in the KL. Otherwise, you would have had a worse distribution. And let's look at, people have argued that GANs are good at generating data that look very realistic because of the implicit assumption on the distribution we are learning. Remember I said that on GANs, you only use a latent and pass that through a neural network and take the output of the neural network as your sample. So that's a very expressive distribution. It's called an implicit distribution, and people have attributed the performance of GANs to that assumption. But here we are showing that that is not the case because we added noise at the output of the network like we do in VAEs. And we notice that you actually get, by doing that, you can, of course, avoid collapse with this entropy thing, but you also don't lose any of the GAN's ability to generate good samples. Here you look at MNIST. On the left, I have real MNIST digits. On the right, top right, I have DC GANs generated digits. And below, I have left lambda equals 0 and the other lambda positive. If you look one by one, and you have time and you go through the digits one by one, you'll notice that psi-GAN generates very good digits when compared to the DC GAN. The digits are easy, so we looked at, MNIST is easy, we looked at stacked MNIST, which has more modes. And here is even more striking because if you compare the true data on the left and the bottom right, which is psi-GAN with lambda positive, you'll notice that it's actually very good. But a better, maybe this is not close enough, a better comparison is looking at the more challenging data. So we looked at CELEB, which is a data set of more than 200,000 set of images of celebrities' faces. And so on the left, still you have the true data. On the top right, you have DC GAN samples, and on the bottom, you have lambda equals 0 on the left and lambda positive on the right. And here, if you zoom in and look closely, actually psi-GAN has better samples. And I think that's due to the fact that when you're doing this entropy regularization, you're able to, of course, you cover all of the modes of the data, but by doing that and doing adversarial learning, you are able to focus on details just as the GAN does. So the goal of this talk was to present this new family of GANs, which you can train in a more stable way, and which you can use to compute log likelihoods, which you were not able to in regular GANs because the likelihood was not defined. You can with this, and then which you also don't have mode collapse because it is specifically trained to say focus on all the modes while not losing sample quality. So if you have some question on this, I'm ready to take them. I think that's all I had. Thank you. Yeah.
Thank you for your talk.
Mm-hmm.
Previous slide, one before. Yeah, this one.
Mm-hmm.
Yeah, talk about how you got the side benefit of handling data imbalances.
Right.
From side.
Yeah.
I don't know if you, because like one thing people do with regular GANs is to do this weighted balance sampling. Okay?
Yeah.
For each batch, you make sure you constrain the sizes of the classes.
Yes.
I don't know if you tried with that to see.
You can do that, of course. That's why one trick people use in imbalance, but I wanted to show that when you train a GAN on an imbalanced data, that's actually another source of collapse.
Okay, so without trying to
Yes, yes, yeah. Yeah. But yeah, that's a good idea. That's usually the trick people use, to use the same data weighting thing. Yeah. Yeah.
So you said you can compute likelihoods.
Yes.
How do your model compare to like normal BAEs or even autoregressive models where you can also compute likelihoods on, say, M?
Yes, literally we are writing the paper for NeurIPS.
Okay.
I have a table set up. We are doing that. But the idea is to use importance sampling as usual.
Okay.
Yes, and there you can ask, okay, then what's your proposal distribution? The proposal is fit via Hamiltonian Monte Carlo, the same one we use to train, to estimate the entropy. And you can also use the Ali Beigan approach, which is fitting the encoder. And in that case, the encoder is automatically a valid proposal for computing log likelihood. But yeah, I'm excited to see what we get compared to VAEs, which are specifically trained to maximize log likelihood. Yeah, but you know what? I expect it to be good, because if you are generating these amazing samples, there's no way they should do worse. Yeah, yeah.
And another question is, there's other work in GANs to kind of prevent mode collapse.
Yes.
If there's relations between those and what you're proposing, or,
Yeah.
or I mean, do you think this is the one, or why?
I'm not saying this is the one, definitely not. But we are comparing to this new, that was NeurIPS 2018, Burgan, and there's vegan also.
Yeah.
But I will add those numbers. But what we have on top of those is that we don't focus only on mode collapse. Now we also, our initial goal was mode collapse, but we end up having all these other desirable features, which is stable training. Like the SciGAN never had instabilities. When I run it compared to DCGAN, say on MNIST, DCGAN after 2016 epochs, it fails. Discriminator is always 111. For SciGAN, I never observed that. So you can run it longer anywhere you wanna, yeah. And we also get, you get being able to compute log likelihood, you get stability on top of mode collapse. Yeah. So I encourage this one.
Are you gonna release the code?
Huh?
Are you gonna release the code?
Yes, yes, yes. Yeah, yeah.
No more questions.
Cool. Any question? Cool. Thank you.